In section 1.2, I'll discuss the quantity average speed and how we can use it to describe the rate at which an object moves through a distance. An object's speed is a measure of how fast that the object is moving. And to get used to the concept, I'm going to talk about objects that are moving with a constant speed, which is just another way of saying that the speed of the object is not changing. And for that situation, this is the equation for speed. The speed of an object is represented by a lowercase letter s, and the standard unit for speed is the meter per second. But we can have any unit of length divided by any unit of time to have our unit for speed. But we would always want to use the units meters per second so that we can be consistent with our other units. The d in the equation represents the distance traveled by an object in a corresponding amount of time that we represent with a lowercase letter t. And the units for speed and distance should all be consistent. So for an example, let's say that we used units of centimeters to measure our distance, and we used seconds to represent our time. That would then mean that seconds would have to be in units of centimeters over seconds. All of these units have to be consistent with each other. In physics, we use the term at rest to describe an object whose speed is zero, which is to say that an object that isn't moving. So an object that's at rest is not moving, has zero speed. In this example, we have a car that's traveling with a constant speed of 11 meters per second for 4 seconds. Part A asks, what is the distance that the car travels? And Part B asks, what distance would the car travel in 8 seconds? We should begin by identifying the important information given in the problem and the unknown values that we're going to need to find. I'll highlight them here. I highlighted the important information in Part B in green to point out that there's going to be a shortcut that we can use to solve this part of the problem. You can usually recognize this sort of situation when different parts of the problem ask you to calculate the same quantity, but by changing only one of the givens. And usually they will change the givens in a way where we increase or decrease by some nice factor. And in this case, we multiplied the time that was given in Part A by 2 to get the time that we're given for Part B. So we're going to use that nice factor along with a shortcut to figure out the answer for Part B. For Part A, we can use the equation for speed, which is distance over time, and we can rearrange the equation to solve for distance. To do this, we need to do the same thing to both sides of the equation, and so we can multiply both sides by t. That eliminates t from the right-hand side and leaves us just with what we're solving for, the distance. So distance is speed times time. I can then insert the values that are given in the problem to calculate the distance traveled in 4 seconds as 44 meters. And notice that when I give my answer, I always give it along with the number and the unit. It is always important to list unit with your final answers. For Part B, we're going to look at the equation for speed, but we want to use this equation to recognize the relationship between distance and time, because we're increasing the amount of time, and if we understand the relationship between distance and time, we can use that to figure out the new distance. And what I'd like to point out is that we have on the right-hand side a ratio of our values. And then on the left-hand side, we have a constant number. So the situation where you have a constant number equaling a ratio, that is our signal that the distance and the time are directly proportional, which means that whatever we multiply the time by, we're going to multiply the distance by that same factor. If we travel at that same speed for twice the time, then we're going to travel twice the distance. And twice 44 meters is 88 meters. One more way that we could show this, if we know that the distance is directly proportional to the time, then we can use this to set up what I had called a scaling equation. To set up a scaling equation, we recognize that we have a ratio that's always a constant number. So the ratio, distance over time, is always the same. It's the same ratio. So one distance over one time is the same as the new distance over the new time. And we know one distance and one time. We know our second time, so we can use it to solve for our unknown distance. And filling in all of the known values, we arrive with this, which we can then use to solve for the unknown value x. And you can simply do this by just cross multiplying, and that'll again give you the 88 meters, which is the answer to part B. In this next example, we'll consider the situation where you're traveling at a constant speed of 20 meters per second. Part A asks, how long will it take you to travel a distance of 120 meters? And Part B asks, how long will it take you to travel the same distance traveling at a speed of 40 meters per second? Again, we should identify the important information shown in the problem and the unknown values that we need to find. I'm going to highlight them for you. Some things to point out. Both Part A and Part B are asking how long something takes. When a question asks you how long something takes, they're asking you to calculate an amount of time. So both Parts A and B are asking us to solve for time. The other thing that we need to point out is that from Part A to Part B, we're going to increase our speed. And we're increasing our speed by a really easy factor here. We're doubling the speed, right, to get from the speed in Part A to the speed in Part B. That's going to be important for Part B. So for Part A, finding how long it takes, we're going to use the equation for speed. And we need to rearrange this equation to solve for time. So when we have this situation where we're trying to solve for an unknown in the denominator, real neat algebra trick, you can just switch the time, which is the unknown value in the denominator, with everything on the other side of the equation. Right? In this case, there's just one value that we're switching it with, but we're able to do that algebraically. So this is our solution. It solves for time. It's distance over speed. I can then substitute in the values and calculate the value that we needed to find, which was time, and the time here is 6 seconds. Briefly, I just want to show you that the units are the right units because we have meters over meters per second. And meters over meters per second is a second, and it works out to be that because we're dividing by a fraction. Dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so the units of meters are going to cancel out, leaving us with units of seconds. So at the end of a problem, once you put in the known values, if you go through the units to make sure the units end up being what units of what you're trying to find, in this case seconds, which is a unit of time, that's a good clue that you did the problem right. That's called dimensional analysis, and that's just one additional check that you solved the problem correct. For Part B, we can use scaling because we scaled the speed by a factor of 2. And here we have the equation for speed. And if we look at this equation, we should be able to tell that because speed is on one side and time is in the denominator, if we rearrange this for distance, we get speed times time. Well, here we have a product equaling a constant value. And that's the situation that we have when we have an inversely proportional relationship. Here, time is inversely proportional to speed. And we increased our speed by a factor of 2. So if we double the speed, that means we're going to take only half that amount of time to reach the destination, to cover the same distance. And so we could, alternatively, we could set up this scaling equation. And the scaling equation comes from recognizing that speed times time, that product is always the same value. So we can say that one speed traveled for one amount of time is a new speed traveled by a new amount of time. We can then put in the known values and solve the equation for the unknown value x, where we would get 3 seconds just as we expected, right? 3 seconds is half of 6 seconds. We doubled the speed, so it took us half the time to travel the same distance. For situations that involve a changing speed, it's many times is useful to calculate the average speed traveled by an object. Here's the equation for average speed, and I need to point out that when you have this sort of symbol where you have the bar drawn over top of the symbol, that's indicating that we have an average of that value. So the S bar is the same as average speed. It's just a different way to write it. Over here, we have the subscripts I and F, and subscripts are used when we have the same value being used more than once in the same equation. And here we have S as in S average, we have SI that represents the initial speed, and we have SF representing the final speed. Please, please, please use caution when choosing to use this equation. You can only use this equation for situations where an object's speed is changing steadily. And this is the important term right here, that the speed changes steadily, which is to say that it's changing at a constant rate. Later, we'll describe this as an acceleration, but we're not to that in this unit. So for right now, we can just use this whenever we have an object that is changing its speed steadily. In this example, we can compare the average speed of two runners to judge who would win in a race. And because they're traveling the same distance and the time is inversely proportional to average speed, then it's the average speed of the runner who will determine who wins the race. The runner that has the larger average speed will finish the race in less time and therefore win the race. Again, I'm going to highlight the important information. I tried to color code everything dealing with Alex in red, everything dealing with Bill in blue, and then in part C, I highlighted who wins the race because we can use what we decide in parts A and B to answer part C. Here's the equation for average speed. The subscript A is there to represent Alex's average speed. So that's why I use the subscript A to represent the average speed of Alex. Alex, it says, starts from rest. Therefore, he starts with an initial speed of 0. And then he ends the race sprinting at 12 meters per second. That is going to be Alex's final speed. And we can insert those values in. And that equals 6 meters per second. So Alex's average speed was 6 meters per second for the race. Now for Bill, we can use the same equation, but now I'm going to put a subscript B on there for the average speed for Bill. And reading the problem, we see that Bill starts the race jogging at a speed of 3 meters per second. So that is Bill's initial speed. He then finishes the race at 11 meters per second. That would be Bill's final speed. And we can insert those values into the equation and calculate Bill's average speed as 7 meters per second. So we need to decide which runner wins the race, and the winner of the race is going to be the winner with the larger average speed. Alex's average speed is less than Bill's average speed. Therefore, the time that it takes Alex to finish the race is going to be greater than the time that it takes Bill to finish the race. And the winner is the runner who finishes the race in less time. So for the same distance, the winner of the race is going to be. In this example, my family and I are going to be the subject of the problem. The Baileys go on a family walk, and they walk for a constant 2 miles an hour for 30 minutes. Then they stop to climb a tree for 10 minutes, and then they walk back home at a constant 3 miles an hour for 20 minutes. And we want to calculate what is the Bailey's average speed. We can highlight the important information and the unknown value that we need to calculate, but there is one more sneaky bit of givens that we need to notice. The fact that we stop and don't move, that's indicating that we are at rest. And when objects are at rest, the speed is 0. So there's 0 speed for some amount of time. We also need to recognize that we cannot use the equation for average speed that was introduced 2 slides ago. It was stressed that this equation can only be used when speed changes steadily, and the speed is not changing steadily here. What we can do is use the equation for speed, distance over time, and recognize that the speed here is actually an average speed. When I introduced the equation, we were talking about objects moving with constant speed, but the speed here is actually an average speed. An average speed is constant speed for objects that are moving with a constant speed. But here we're not, so this still works, but this one doesn't. Okay, distance over time always works to calculate average speed. This works only sometimes for objects whose speed changes steadily. So if I rearrange the equation by multiplying by t on both sides, we can solve for the distance, and we can calculate the distance traveled in each part of the motion. So in the first part of the motion, we travel with a speed of 2 miles an hour for 30 minutes. And you should notice that I changed the 30 minutes into half an hour. And I did that because we have to have consistent units. And if I put 30 minutes in here, we would have gotten 60 mile minutes per hour. And a mile minute per hour doesn't really make much sense. We really want the units of time to cancel out so that we're just left with units of distance. And in this case, that distance is mile. So in the first part of the motion, we go 1 mile. Then we stop to climb the tree. And since we're at rest, we don't really move. So the walk back is really the only other distance that we need to worry about. On the walk back, we're traveling at 3 miles an hour, and we do that for 20 minutes. And again, I had taken that 20 minutes and I had converted that into hours. And 20 minutes in hours is a third of an hour. 20 over 60 is 1/3. So when we calculate the distance, again, we move another mile. That should make sense. We go 1 mile out. We need to come 1 mile back. And when we calculate the average speed using our new distance, well, we traveled a total of 2 miles. And we did that in 1 full hour. 30 minutes plus 10 minutes plus 20 minutes, that's 60 minutes or 1 hour. And so that is a average speed of 2 miles per hour. And I want to point out one more time because this is a point that confuses a lot of students. Average speed is not necessarily the average of the speeds. The equation for average speed is this one right here. This always works. This is the average speed. This equation, the one that we weren't allowed to use, this is the average of the speeds. And this only works when an object increases or decreases their speed steadily. If we had used that equation, we started out at 2 miles an hour, we ended at 3 miles an hour, and the average of those speeds is 5/2 or 2.5 miles per hour, which was not our average speed, right? The average speed was not equal to the average of the speed. So be careful to use the correct equation for the correct situation.